Alright, so in this chapter we are going to talk about uh, Newton's law of gravitation. So around the year 1665, uh, Isaac Newton, then a 23-year-old uh, student at Cambridge University, made one of the greatest discoveries in all of science. He realized that the force of gravity is a universal force, which means that the same force of gravity which would draw an apple from a tree and make it hit the ground is the force which is responsible for the Earth being in orbit around the Sun. It is also the force which is responsible for the Sun being in orbit around the center of the Milky Way galaxy, and the same force which holds the 400 billion stars of the Milky Way galaxy together. It's these forces are all one and the same. So he realized that gravity is a fundamental universal force, and he came up with an equation to calculate the force of gravity between two objects. Okay, uh, legend has it that an apple, uh, Newton was just walking along and an apple fell from a tree and hit his head, and all of a sudden Newton had an epiphany and figured out gravitation. But the reality is actually a lot more complicated. Basically, I'll just give you a brief overview of the historical situation at that time. So, going back to very, very early times, uh, like when we were cave men and women, people would look at the skies and then they would be really fascinated and try to understand what was going on with all these different spots of light in the sky. So, this fascination with astronomy has been part of us since the very beginning. But one thing that has puzzled people to no end is regarding astronomy is not the all the stars that you see in the sky, but specifically 5 points of light. So these 5 points of light have been puzzling people for centuries and millennia. Can you guess what these 5 points of light are? The answer is they are what we currently call Mercury, Venus, Mars, Jupiter, and Saturn. So the planets. So these things have been fascinating people for a very long time. Like now you might wonder why were people so fascinated by the planets? Well, suppose you go out tonight and take a look at uh, any of the planets, Jupiter or Venus, and or Mars, and keep and keep you decide to track its position in the sky. Uh, Suppose you track Jupiter's position every day. What you're going to find is that Jupiter is gradually moving across the sky, and in a few weeks you might think that okay, I finally have a hang of what it's trying to do. It's moving in that direction, but then you will find that it's slowing down, right? It's moving in the same direction, but it's slowing down. Then after a while, it will start moving back, and then you'll be like, oh, so it's not moving in that direction. Now it's changed its mind and wants to go back, and so it will go backwards for a while, and then again it will start slowing down and then start moving forwards. So the motions of the planets are not simple in the sky. So they have rather complicated motions through the sky, and people were really, really puzzled by this. They wanted to understand the big picture, like why do planets move the way they move? In fact, the name planet comes from a Greek word which means wanderer. Okay, so if you fast forward to the time of Aristotle, Aristotle came up with a theory about why the planets move in a certain way, move the way that they do, and that theory was the geocentric model, where the Earth is the center of everything, and the Sun and the planets all orbit, and the stars, everything orbits the Earth. We know that that's wrong, but that geocentric model lasted for a good 1500 years or so. And finally, it was people like uh, Copernicus and Galileo and Kepler who realized that uh, the geocentric model is wrong. In, in fact, the world is heliocentric in the sense that, or rather, the solar system is heliocentric in the sense that the sun is at the center and the planets, all the planets, including the Earth, orbit the sun. Now, between the years 1609 and 1619, Johannes Kepler finally came up with three laws which describe the motion of the planets very accurately. So I'll just briefly tell you what those laws are. These laws are described at the end of of chapter 13, but you are not really responsible for them for exams. So I'm just describing the laws now, just to give you as part of the historical survey. So the first law says that planets orbit the sun in elliptical orbits with the sun at one focus. So the sun is right here, and the planet will orbit the sun in an elliptical orbit. So if you go around in an ellipse like this. Okay, so that's the first law. The second law essentially says that it's a statement about the speed at which the planets orbit the sun. And it says that if a planet moves from here to here, the area of the wedge that it traces out, suppose it traces out this area in time delta t, then in time delta t at any other part of its orbit, it will trace out the same area. So that means in a certain amount of time delta t, the area of the wedge that it's tracing out will remain constant, right? So in the same amount of time delta t, it might trace out another area over here, and that will again have the same area as all the other wedges traced out at the same amount of time. So again, I'm going over this pretty quickly because you're not really responsible for it. One consequence of the second law is that when a planet is closer to the sun, it orbits rather fast. When it's far away from the sun, it orbits rather slow. All right. The third law says that there is a definite mathematical relationship between the time period of a planet and the semi-major axis of the ellipse. So the major axis is this. This would be the major axis of the ellipse, and half of that is the semi-major axis. That is written as A. So there's a definite relationship between the time period of the orbit, which is the time taken to do one full orbit, and the semi-major axis, which I'm calling A. And that mathematical relationship is that t squared is proportional to a cubed. So this is the third law. So these were Kepler's laws. And they seem to explain all the observed locations of the planets very, very accurately, right? So people knew that these laws are true. However, nobody understood why they're true. So why does a planet go around in an ellipse? Why is the second law true? Why is t squared proportional to a cubed? These are questions that even Kepler would not be able to answer. He would just, if you asked him why these are true, he would just say that, look, here is hundreds of years of data. These laws fit all the data that's available. Okay, so one question in the minds of all the smart people at the time of Newton was, why are these laws true? So everybody wanted to find out a deeper reason why these laws are true. And even though Newton was just a college student at that time, and he was thoroughly bored with all his college courses, his mind was preoccupied with this. One of the problems that his mind was preoccupied was this particular problem. Why are Kepler's laws true? So around the mid 1660s, the horrible plague of London hit. It was raging in full force. People were dying in record numbers. In fact, people were dying so fast at that time that uh, there were bodies piled in street corners because people couldn't. It wasn't possible to dispose of the bodies um, fast enough. And all universities and all places where people gathered were closed. So Newton went home, and he spent a year and a half at home and engaged in intensive study of this particular problem. And in 1660, around 1665 or 1666, he came up with his law of gravitation. So, what does the law of gravitation say? It says that if you have 2 point, here is the law. It's this little simple little equation. It basically says that if you have 2 point masses, m1 and m2, and they're separated by a distance r, then the gravitational force between these two masses is given by this equation, g times m1 m2 divided by r squared. What is g? G is called the universal gravitational constant. So it's a fundamental constant of nature, and the value of g is 6.67 times 10 to the negative 11 Newton meter square over kg square. Now notice that we had a separate g. And those of you that are learning this for the first time, notice that we had a separate g, the acceleration due to gravity, which was approximately 9.8 meters per second square. That's different from this g. We will see how these two g's relate later on. But this capital G is the universal gravitational constant, and it has this particular value, 6.67 times 10 to the negative 11 Newton meter square per kg square.